Now we're going to talk about how much energy is transported by a sinusoidal wave on a string in one wavelength. In order to do that, let's take a look at a portion of the string here that has a mass dm and remind ourselves that this part of the string, while transporting the wave, must be moving up and down, performing simple harmonic motion during the transfer of the wave. And why is this performing simple harmonic motion? Because we have an external agent that's the source of energy that is providing energy into the system. So by moving up and down, creating these sinusoidal waves, doing work on the string elements. So because I have this motion, a simple harmonic motion, if I concentrate on one wavelength of this wave, so starting from here, ending here, basically I have ended up in one wavelength, and there has to be a total energy, kinetic energy and potential energy, total mechanical energy transported by this string in one wavelength. So how can I write the kinetic energy of this component of the string which has mass dm? Well, the kinetic energy that is carried by this part of the string is dk, and it's equal to 1 over 2 dm times vy squared, where y is this axis, the axis on which I have the simple harmonic motion. Now I ask myself, do I know what dm is? Well, dm is equal to, if this is my x-axis, mass per unit length, mu times dx. So mu is my linear mass density, and if it's a uniform string, uniform implies its mass divided by the total length of the string, remember. So I have dm is equal to mu dx, and if it's a sinusoidal wave that we're talking about, then I have the wave function y of xt is a sine kx minus omega t plus a possible initial phase that describes this wave. Let's say that this picture was taken at time t is equal to 0 and my initial phase phi is 0. So that with these two simplifications, t is 0, phi is 0 degrees, I have the wave function given by a sine kx. Then what is the velocity, transverse velocity of this string element? It is derivative of y with respect to t. So evaluated at t is equal to 0, phi is equal to 0. The derivative is minus a omega cosine kx minus omega t plus phi, but because t and phi are 0, this is going to be equal to minus a omega cosine kx. Alright, so I can write the kinetic energy of this element here, dk, is equal to 1 over 2 mu dx, which is its mass, dm. So dm is equal to mu dx. And then I have Vy squared, a squared, omega squared, cosine squared, kx. And what I would like to know is how much energy is carried in one wavelength. So k lambda is the integral of all such elements where x goes from 0 to lambda. So what is this integral? What is the total kinetic energy carried in one wavelength? It is 1 over 2 mu a omega squared integral over one wavelength cosine squared kx dx. And now I remind myself that I have the following relationship between cosines and sines. Cosine 2kx is equal to 2 cosine square kx minus 1. So for this one I can write 1 over 4 mu a omega squared integral from 0 to lambda 1 plus cosine 2kx dx. So let's perform this integral. I obtain k lambda is equal to 1 over 4 mu a omega squared. I have x plus 1 over 2k sine 2kx. This has to be evaluated between 0 and lambda. So this is going to be evaluated between 0 and lambda, and I will obtain 1 over 4 mu a omega squared lambda minus 0 plus 1 over 2k sine 2k lambda minus 0. So what is sine 2k lambda? Let's take a look at that here. Sine 2k lambda is sine k, remember, is the wave number, which is 2 pi over lambda. So this will be 4 pi over lambda times lambda, sine 4 pi, which is 0. So this part will give me 0, so I'm only left with lambda. So the total kinetic energy carried by this wave in one wavelength is going to be equal to 1 over 4 mu lambda omega a squared. Now I have to do the same exercise for the potential energy carried by a string element. Okay, now for the potential energy, I know that the potential energy is given by 1 over 2 kx squared. And remember, in my simple harmonic motion, I had x double dot is equal to minus omega square x, where omega square was equal to k over m, or what I'm calling k is m omega squared. So for the when I apply this information to the simple harmonic motion that I have to consider here, so this is basically recalling from my previous study. I'm going to have a potential energy du that's equal to 1 over 2 omega square dm multiplied with y squared. So this will be corresponding to my spring constant k here, it's omega squared dm times y squared. Y is the displacement from the equilibrium position. So this will be equal to 1 over 2 omega squared. For dm I can write mu dx, and for y, what can I write? Y is equal to a sine kx, so it's going to be a square sine square kx. Therefore I will obtain a du, it's 1 over 2 mu a omega squared sine squared kx dx. And in order to find the total potential energy carried in one wavelength, I have to integrate this from 0 to lambda du. I will obtain 1 over 2 mu a omega squared integral from 0 to lambda sine squared kx dx. And this time I'm going to use the following relationship. Cosine 2kx is 1 minus 2 sine square kx. So I find that the potential energy carried in one wavelength is 1 over 2 mu a omega squared integral from 0 to lambda 1 minus cosine 2kx divided by 2 dx. So this will be equal to 1 over 4 mu a omega squared integral from 0 to lambda 1 minus cosine 2kx dx. So let's perform the integral. I obtain 1 over 4 mu a omega squared. The integral gives me an x, and then I have 1 over 2k sine 2kx, and this has to be evaluated between 0 and lambda. And similar to the previous case, I will just obtain from this integral 1 over 4 mu lambda omega a squared. So the total potential energy carried in one wavelength is 1 over 4 mu lambda omega a squared. It's exactly the same answer as the kinetic energy carried in one wavelength. So the energy is shared equally between potential and kinetic, so that I have the total mechanical energy carried in one wavelength is kinetic plus potential is going to be equal to 1 over 2 mu lambda omega a squared. So that's the total energy carried in one wavelength. You may be wondering why I'm putting these parentheses like this. So I want you to just remember that mu is mass per unit length. The dimension of mu times lambda is mass, and the dimension of omega times a is dimension of velocity. It's the maximum transverse speed, right? So grouped this way, this should remind you of 1 over 2 m v squared, where m is going to correspond to mu times lambda, the mass of one wavelength, and omega a is the maximum speed, transverse speed, in the simple harmonic motion of the string elements. Now, if I just look at the power, the rate at which I'm delivering energy into the system, the power P, rate of energy transfer, then I ask myself, how long does it take to transfer this much energy the energy carried in one wavelength, I know that this energy moves from one location to the other, to the next location in one period, from one wavelength to the next wavelength, that's in one period. So I have 1 over 2 mu lambda over the period omega a squared, and then I remember the propagation speed of the wave, not the transverse speed of string elements. It's the lambda wavelength divided by the period. So I find that the power rate of energy transfer is 1 over 2 mu v omega a squared. So this will be my final answer for the rate of energy transfer in the sinusoidal wave on this string.